Perfect. Hi everybody. Thanks for coming along to my talk. My name is Kieran Barrett and I'm an applications engineer from Analog Devices. I'm here to talk to you today about a novel power detector application circuit. Sorry, can you hear me? I'm here to talk to you today about a novel power detector application circuit that monitors system return loss, or BSWR, without the need for calibration across frequency, using just 3 main Analog Devices components. So as this is a power detector application circuit, I'd just like to give you a brief overview for some of the detectors currently available from Analog Devices. So we offer a broad range of different detectors, now even more so with the acquisition of Hittite in 2014. The 2 major portfolios of detector are the RMS responding and non-RMS responding detectors. And these are used in a variety of different infrastructures such as comms infrastructure, aviation and military applications. And as you can see from the graph there, that we have an extensive portfolio that varies from sub-megahertz to greater than 40 gigahertz, and power ranging from 30 dB to 100 dB. We're currently expanding our portfolio to develop detectors for a higher power range above 10 gigahertz, and also develop detectors above 40 gigahertz as the applications emerge. So just to give you an overview for the circuit, there's a highly versatile circuit for monitoring return loss in a wire-to-wireless communication system. The unique calibration-free feature means that there's no calibration necessary at each frequency of operation prior to measuring return loss. So it's implemented in a simplistic design using just 3 main Analog Devices components: a broadband envelope power detector, a fast-responding RF single-pole double-throw switch, and an ultra-low power consumption 12-bit ADC. So you might be wondering, why are we interested in monitoring return loss? Well, return loss is an important parameter in wire-to-wireless communications, and it essentially measures the level of transmitted power to reflected power, unwanted reflected power in the opposite direction. It has implications in transmission efficiency, and extreme cases can also result in PA or circuit damage if the return loss is considerably poor. So if we're able to monitor return loss continuously, we can prevent damage to the circuit from occurring, and we can also improve transmission efficiency as well. Common causes for poor return loss can include damage to the antenna, so this could be from a lightning strike or other weather conditions, and also PA to antenna mismatch, so if the antenna has been poorly terminated to the load, to the transmission line. So just to begin the circuit description, an RF signal is fed through a directional coupler through to an antenna load. Depending on the position of the RF switch, either the forward or reverse signal is coupled to the input of the power detector. So this is a coupled portion of the original transmitted signal, and the coupling portion is approximately 10 dB. So in the position 1 of the switch shown below, we can see that the forward signal is fed through to the input of the detector, while the reverse signal is terminated in 50 ohms for non-reflective coupling. When the switch position is then toggled, the forward signal is terminated in 50 ohms and the reverse signal is fed through to the power detector. So I'd like to talk a little bit about the signal coupling, as it's an important concept in this design. The RF couplers, there are a variety of different transmission line couplers that we could have chosen from. The 3 main types would be the connectorized, surface mount and PCB trace. The connectorized coupler was the one that we decided to go ahead with because of its increased power and frequency capabilities. So we could use it for many different applications, and also the fact that it allows versatile design. So we can readily disconnect and reconnect different couplers and interchange as the application demanded. The coupler we decided to go with was a Marquee microwave directional coupler. As you can see, it's unterminated at its coupled ports, which effectively provides us with a bidirectional operation. So since we are externally providing the 50 ohms through the RF switch, the coupling factor is 10 dB. And one of the important parameters when deciding on any coupler to use is the directivity. So the directivity relates to the isolation between the 2 coupled ports and also the coupling factor as well. So if the directivity is not high enough, we see an inaccurate measurement of return loss. As a general rule of thumb, we want to get 15 dB higher directivity than the return loss being measured for accurate measurement. The RF switch we use is a simple general purpose RF switch with high isolation, has a frequency range of DC to 28 gigahertz, and it also has internal 50 ohm resistors for non-reflective termination. So that was chosen based on its frequency range and the non-reflective characteristic for measuring return loss. The next stage in the circuit operation then, we have the two components, the power detector and the ADC. So the coupled forward or reverse signals are fed to the input of the power detector, while then on the output of the power detector, DC output voltage appears, which is the instantaneous RMS amplitude of the signal applied to the input. This is then stepped down using a simple unbuffered resistor network and oversampled using the ADC and sent to the PC for communication. So it's converted to a digital code forward and reverse, and then that's used to calculate the return loss. The power detector is called the ADL 6010. This is a broadband power detector for many different applications because of its frequency range of 500 megahertz to 43.5 gigahertz. It also has a dynamic range of 45 dB, ranging from minus 30 dBm to plus 15 dBm. It also has a lower power consumption of 8 milliwatts. So it's chosen mainly because of its wide frequency range and its dynamic range. So the ADC used is a simple 12-bit architecture ADC with an integrated 2.5 volt reference. The sampling rate of the ADC is up to 1 megasamples per second, and also it has a low power consumption of 1 milliwatt. You can also get reduced power consumption for reduced throughput rate. So this ADC was able to resolve all the voltages within the range of the power detector output. So just to describe briefly the calibration-free operation. So we start off with the transfer function there shown, number 1, the equation 1. And you can see here there's two frequency-dependent components. The geometrical slope and intercept of the transfer function, and this is represented on the two graphs on the right. You can see the upper one is scaled volts in, volts out, and the lower one is scaled power in dBm versus volts out. But they essentially describe the same effect, is that the frequency variation causes a variation in the transfer function due to these frequency components, M and C, the slope and intercept. And equation 2 then just represents the overall transfer function of the system with the ADC and power detector combined. So M prime and C prime are the combined slope and intercept of the ADC and power detector. So in this circuit, it's a calibration-free operation, so it doesn't actually rely on the slope or intercept of the power detector or ADC to calculate return loss. Instead, equation 3 here, as you can see, has been derived from equation 1, and you can see that the slope and intercept are not included in this calculation. These have been cancelled out in the derivation. Well, actually, it's worth mentioning that M has been cancelled out and C is negatively small, so it doesn't need to be included in the calculation because it doesn't affect the return loss calculation. So just to give you an idea for the algorithm itself and how it samples. First of all, the forward coupled signal is fed to the detector input. This is then oversampled 500 times and averaged to get a code forward for the ADC. The switch position is then toggled again, and the reverse signal is fed to the detector input. This is then oversampled another 500 times and averaged to get the reverse code. So both these codes are then sent from the interface to the PC for calculation of return loss, and this is updated in the software display live. And the time parameters are, it takes 500 microseconds to measure the forward code because it's 1 megasamples per second ADC and 500 samples. And we have a 400 microseconds delay to toggle the switch. This is a delay from LabVIEW and not from the switch itself, which switches much faster. Another 500 samples for the reverse, and then LabVIEW then calculates the return loss with a delay of approximately 750 microseconds. This is continuously updated in the software display. So it's a good idea before measuring return loss to get a feel for the different levels that you can operate within at each stages of the circuit. So without getting into too much detail, these are the different, each of these 5 stages are different stages in the circuit. So the forward power range, you can see the lower limit there of 0 dBm. This is for a 20 dB return loss measurement. So because of the range of the detector from 15 dBm to minus 30 dBm, we're limited to 20 dB return loss and 10 dB coupling factor, and that would take it down to minus 30. The forward power range at the detector itself is just simply scaled down by the coupling factor. And then the middle one then, that's the forward power range of the, that's the detector range, complete detector range, which is plus 15 dBm to minus 30 dBm. The reverse power range is essentially the same, and then the reverse power range at the coupler is scaled up from the coupling factor. So the measured results here, this was done by effectively applying a 10 dB attenuator to the output of the coupler to simulate a 20 dB return loss. So we have a 10 dB forward attenuation, 10 dB reverse. As you can see from the graph there, these manual results were gathered with a 2 GHz input signal, and it swept from -25 to +27. We can see the operating range verifies with the level plan, which is 0 dBm to +25 approximately. So you can see across that range we're getting a consistent 20 dB return loss being measured. So below 0 dBm we're approaching the lower limit of the detector, which is -30, so you can see it's falling off, and above 25 dBm we're reaching the detector upper limit of +15 dBm. This is just a high-level block diagram of the circuit itself. We can see here all the main components on the board. Everything contained within the dotted line is the evaluation board itself, and you have some CMOS control circuitry controlled by GPIOs to toggle the switch periodically, and the coupler is mounted off the board. So this is the board itself. It's currently available from analogdevices.com/CN0387. Points to note is the coupled coupler inputs there shown on one. So the external coupler connects to those, feeds through to the RF switch, to the power detector, and then finally to the ADC. And the interface board is then used to communicate with the PC. So to conclude, this has been a linear in volts RF detector which can measure up to 20 dB return loss within a frequency range of 500 MHz up to 28 GHz. Operation is completely calibration free due to the simple ratio metric of forward to reverse codes, and has a total power consumption of 9 milliwatts. Higher input power levels can be tolerated if we add attenuation stages after the coupler stage, or also we could change the coupler for a different coupling factor coupler. But a key important parameter when measuring return loss is the directivity, and that needs to be sufficiently high enough to get accurate return loss measurement. So that's it from me. Thanks for listening to my talk, and if you have any questions about this, feel free to ask, or if you have any other questions, please feel free to go to the Analog Devices booth 1519 at any stage during the conference. So in a real life situation, you're asking how does it? So this evaluation board isn't necessarily to be used in the situation, but it's simply to evaluate the performance of these components. So in a real life situation, this is something you could implement on your own circuitry. So it's not something that would be directly used as such, but the calibration free feature would still apply, and it would still have all the same characteristics. Is that okay? Okay. Thanks.